Hello, everyone. My name is Andrea. I work for NVIDIA. I'm going to kick off the SCADX day. So it's like, yeah, there are 3 talks about SCADX now. And yeah, I'm sorry if you're not interested in the topic. Blame Yuri and Tomas. They did the schedule. So in this talk, I'm going to do like a little recap of what's happening, the things that we are doing, what we're working on, future plans, good things, bad things. We'll see. I'm not going into details of these. I mean, or you should know what SCADX is. It's been merged in 612 now, so now it's upstream stuff. We're doing most of the kernel development in Tejun's branch here. And we also have, we don't have the schedulers in tree, like in the kernel tree, but we have this repo on GitHub where we maintain basically all the schedulers, libraries, tooling. And we decided to do that, well, of course, for the tooling, it makes sense, but for the schedulers as well, to have more freedom to accept new people doing experiments. So we're not super picky with reviews. We accept schedulers. Like, you still get a review, and we will let you know if we find problems or so. So you get a review, but basically the agreement is that each other we can share ideas and we can steal each other ideas, of course. So yeah, this is a list. Like, we have more schedulers, but some of them are experimentals. This is probably the list of the more production ready. Especially like this one, LAVD. We have Changu here, who's the author. LAVD is more oriented on gaming. We have BPF-land is more oriented, again, latency, responsiveness. Flash is a scheduler that tries to prioritize like audio, multimedia stuff. These two are actually quite similar. This is the scheduler that Meta is using in production. And it's highly configurable. You can have a JSON file where you define all your partitioning and rules and time slices and prioritization, preemption rules, whatever. And then when you start the scheduler, this JSON is translated into partitioning rules. And we have Rusty, which is like a kind of an hybrid scheduler, meaning that most of the hot paths is implemented in BPF, and it has the load balancer implemented in user space. And basically, the information is exchanged between user space and BPF using BPF maps.
And user space is written in Rust.
User space is written in Rust. Yes, thank you. And that's why it's called Rust. Now, most of this, I think, okay, all these schedulers, actually all of them.
This is your list of governors.
Yes. Yeah, all of them are written they're hybrid, but they have a Rust part and a C part that then it's compiled into BPF. The Rust part from most of them is just the initialization. You parse some parameters and you populate some BPF maps, and then you pass the control to the BPF scheduler, and most of the logics and hot path is implemented in BPF. But there are others, like yes, Rust is one of them, where the load balancer is in Rust in user space. Rustland is kind of the extreme opposite condition, where the BPF part is like a thin layer, where all the callbacks, because if you implement a BPF scheduler, you just need to implement callbacks. And in Rustland, the callbacks are just passing all the events to a user space task that implements the scheduler. So there's a whole Rust API, there's a Rust crate that you can use to implement your scheduler fully in user space. And in fact, I like to define Rustlet not as a scheduler, but just more like a framework. There's actually a Rust crate called Rustland Core that you can use. You can import in your project and have and you implement your scheduler in Rust, but not Rust. It's not Rust for Linux. It's a user space Rust. we also started to do some, because most of these schedulers are like latency or gaming, desktop oriented. We don't have many use cases for server workloads, except for Rusty maybe. So I started to play with with a tickless scheduler, meaning that, of course, I use together with no hairs full to isolate some CPUs. The idea is to have like a pool of central CPUs or scheduling CPUs that they basically manage the scheduling events. They are dedicated to do scheduling, and the rest of the CPUs are like dedicated to run isolated tasks, let's say. It's kind of an extension to No Hairs Full. The cool thing is that on the central CPUs, I can run multiple BPF timers. So potentially I can have a different scheduling tick with a different hertz across the other CPUs. Or I can even isolate only a certain subset of CPUs and keep the others like regularly scheduled, stuff like that. Yeah, maybe if there's time, Joel will cover more about this topic, so I don't want to insist much. People started to do bindings to SCADX to different languages. Of course, C is well supported with libBPF. Rust is also well supported because most of the production schedulers that we have are hybrid Rust and C. There's someone that decided to go with the crazy path of the guy over there of doing the Java connections. So you can implement a scheduler in Java that would interact with the BPF part, of course. This is work in progress. People are looking. Go is actually in a good state. I think it's already usable. There's this project on GitHub. Someone showed up in the office hour. We were doing a SCADX office hour, mentioning that he was working on the Python binding. So it would be cool to be able to write a scheduler in Python, but I don't know what's the status of this project. Just a few things about distros. Distros are catching up, of course, now with SCADX available in 6.12. As soon as distros are updating to the new kernel, we will have support. Special mention to CacheOS, which is it's a minor distro, but they were very proactive at like merging SCADX. I think they started merging SCADX with 6.7 or 6.8. So the early patches, they already merged that, and they provided us like a lot of feedback. And this distro is like full of gamers. So gamers are like so paranoid. They want to get, the highest number in the benchmarks, even if it doesn't mean anything, but they're happy doing these benchmarks. The good thing is that they did a lot of testing for us. So they were able to catch so many bugs, so many regressions, and that was very helpful. So even if the main purpose, the main goal was to, get the higher number with the gaming benchmarks, at the end, it was very helpful for us just because of the feedback. Ubuntu, this is the next upcoming Ubuntu, will have SCADX enable, and the other distros are also catching up. Oracle is planning to invest a lot on SCADX. I don't know the details of this, but that's what I heard. We on the GitHub repo, the one that contains all the schedulers, we have also a kind of CI/CD way of testing SCADX. Both the core, we test these kernels, and we also test. We test all the schedulers against all these kernels. We just sync with the latest branch. And we're running GitHub workflows. If you're not familiar, it's just a Docker thingy that runs. And we're using mostly stressed-ng to simulate workloads. And we're using virtmin-ng, that, if you're not familiar, is a tool that allows you to run the kernel using the host file system, which is mounted in read-only, and for the writes, it mounts overlays on top of the host file system imported inside the guest using Virtio FSD. So it's really fast. You can do writes, you can mess up your file system, and then you stop the machine and nothing happens. And it's really convenient because you can you can prepare your tools and scripts and whatnot in your host, and then you just, kind of / the kernel almost. So we are using that for the CI/CD. We don't have performance regression tests. In fact, if you guys have any idea what kind of benchmark suite, whatever we could use, would be happy to receive suggestions. Because right now we just stress NG and we see if the system explodes. That's the only thing that we test. We have a Slack channel. Community is mostly hanging out here. You are welcome to join. And last night I think we were talking about it's really hard. So if you want to design a good SCADAX scheduler, it's really, I think we did a really good job with documentation. Like if you go on the source code, it's very well documented in a proper way, but it's really hard to catch all the little details. So I think a good way, if you want to become familiar with SCADAX itself, like designing schedulers, to just join the Slack channels and attend office hours. Maybe that's my recommendation. And again,
no IRC channels.
No, we don't have IRC. I'm a big fan of IRC, so I found that was the way to communicate. So it's not my decision.
Like
emojis, yeah. We share all the little hearts and it's Julia.
So you showed a bunch of different scheduling policies before. I wonder if there's some repetition between them.
Repetition, you mean they're sharing code, or they
should be sharing code or something?
Yeah. So we're trying to do a good job for the Rust part. So if we see that there's a pattern that we're doing pretty much the same things, we try to move that into a Rust crate or a Rust library. We actually have a Rust crate that is called topology, where we abstract all the topology information. So LLC, NUMA nodes, we're starting to add the concept of preferred cores. And of course, that can be consumed from user space, the user space part of the scheduler, and you can push the information that you need into BPF maps, and then you can consume that from BPF to take the scheduling decisions. So that's how we try to reduce the code duplication.
So can the other schedulers use that, or just?
I think so. LAVD, BPF, and Flash, they all of these are using the topology crate, for example. And there's also code duplication on the BPF side, and that's also something that we are working on, because the idea is to, now that we have given the possibility to offload the kernel into BPF, we are trying to bring some code back into the kernel, meaning that SCADAX, the core, implements on its own scheduler internally. So you can load a BPF scheduler that is empty. You just, you have an empty template, doesn't implement any callback. That works already because it's using the default built-in policies it's a FIFO basically. There's a default time slice assigned. It's actually a round robin, not a FIFO, but it's called FIFO. And there's a default time slice. There's a built-in default idle CPU selection policy. There's not a default load balancer, which is something that we should probably implement, because now there's just, by default, there's a global run queue. Which is not really global. It's per NUMA node, but per node global run queue, let's say. So that's how we're trying to avoid code duplication.
What's the point of the SCX tickless thing? Because the point of Norris pool is to get away the scheduler in the end.
Sure. You can use Noher's full and then make sure that you have either 0 or 1 task on each CPU, and then you can guarantee like isolation, or you don't have OS, or you reduce OS noise. The point of this one is to have a way to like have more freedom in the scheduler to say, okay, I want a pool of CPUs where I want to guarantee a certain quality of service of isolation. So I may allow certain tasks to jump on these CPUs. So having like soft isolated CPUs, I don't know. You can probably do that. I mean, tickless, you can probably do the same with C groups and user space rules.
I think, for
it's
example, OCP solution, they do that.
It's totally doable.
Sets and then they essentially dynamically
Yeah.
change them. But I guess you might be, I guess we are fighting against non-perfect isolation, and this is, I don't think that's...
Yeah, exactly. Another thing is like, for example, in tickless, you can allow K threads to go together with another task. And when it happens, the tick would be reactivated in the kernel tick, the in-kernel tick. But one thing that you can do, you can run BPF timers and say, the tick is reactivated, but I can decide to do the preemption or stop the task at a certain frequency versus like using the config hertz. I don't know, something like that.
Just so I understand this correctly, I'm trying to grasp it. So basically you have like really no hertz full going on a CPU. So it ticks off. But then you actually schedule different tasks on it because SCADX is now, so the kernel thinks it's only one task. So when it's one task running, it's going to say, oh, we could disable tick because it's one task. Now the scheduler or the BPF SCADX is now just, okay, I'll just put this one task, and it actually schedules one task at a time. What about the accounting of those tasks? How do you handle that?
What do you mean with accounting? Like, because that's what's happening. Yes.
Because you do have like, if you're doing that, time, when you do a time, how long has it been? Usually like there's accounting going on for how much time.
Yeah, so that's it's up to the scheduler. Right now we have callbacks that are called when a task is starting on a CPU. It's the ops running, and we have ops stopping when it stops on a CPU. You can implement your own accounting in BPF by catching these two events. We also have runnable and questions. That is like usually the task workflow. I actually have a slide with that. Let me go a little, right here. So when a task becomes runnable, this is like the wake up, let's say. It becomes runnable, and then inside this path, you have multiple running tick stopping, running tick stopping, running tick stopping. You have running tick stopping when you expire your time slice. And then you go back here if you don't sleep. If the task sleeps, it becomes question, and then when you have a wake up, it goes back here. So if you catch these events, you can implement these callbacks and account for the time that you're using the CPU.
That's also kind of like how no-hertz works, right? Like you don't need the tick to do any kind of accounting. Like you just turn it off. And then the other point I wanted to make was tickless stuff. Like you schedule it with an infinite time slice. That's how it works. You tell BPF.
Oh yeah, exactly.
You tell BPF like just schedule this and as long as you want. And when the task goes to sleep, I guess.
That's an internal SCADX rule. It's like when you insert a task into it's called dispatch queue. It's basically a run queue. When you insert a task, you can decide how long, like you can decide the time slice. And if you assign an infinite time slice, it would not call the tick, this one. So you're basically disabling the tick. But that's not the kernel tick, it's the SCADX tick, which is based, of course, on the in-kernel tick.
So the funny thing is, if you don't use tickless and you use some of the SCX scheduler and you put the CPU and no hertz full, and there's only one task running, the tick will still not be turned off because it has to go back to BPF on every tick and ask it, do you want to run something else? So by design, it cannot turn off the tick. But with the tickless scheduler, you can, because you tell BPF like I want an infinite slice, it doesn't need the tick. So I actually tested this and I verified that.
So you have to boot the kernel when you go exit for that.
Yeah, you still need to do all that.
Yeah.
And then the boot parameters and all that.
Yeah, exactly. And since I'm here, like I mentioned, DSQs. So internally, it works with this, like each CPU as a dispatch queue or DSQ. This is just a FIFO. The built-in DSQs are FIFOs, and if you insert a task in one of these, it would be automatically consumed. The consume is happening like in the scheduler balance callback. So it's consumed from the local DSQ, and the task will run. You can't run a task directly. You always need to pass through the local DSQ if you want to run a task. There's also a built-in global DSQ that you see in BPF. You see these as a single queue, but on the backend is actually split into multiple queues, one per NUMA node. One thing that I would like to add at some point is to have an option, maybe to set this one as a per LLC, for example, or define a different kind of granularity. But if you don't like these, I mean, you can create any amount of arbitrary user dispatch queues, and then you define the semantic of the DSQ in your own scheduler. Like you can say, I consume from this DSQ only from the first 3 CPUs. I don't know. Or I consume only from a single CPU. And then it becomes a regular run queue, let's say. And so the built-in ones, the built-in DSQs, these and this one, they can only work in FIFO mode. There's no way to use them otherwise. This one is, there are 2 modes of operation. You can use either as FIFO and it becomes like one of these, or you can use like a kind of a priority queue. If you use the priority, you pass an additional value that we call vtime. But actually what it is, it's like behind that there's an RB3 and it uses the vtime to order the tasks according to the vtime. So you can use you can do vruntime scheduling or deadline-based schedulers using simply by inserting a task and passing a different vtime value. You don't have to re-implement in BPF the whole RB3 logic. Otherwise, it would be tricky. But good luck with a verifier. So that's why we have the in-kernel part for the backend here. And so what can you do? You can do task management. You can say, this task goes here, this task goes there, and you can decide how long a task goes. You can assign a time slice or an infinite time slice in the case of the tickless. There's a built-in CPU selection policy that you can optionally use. If you don't implement the ops select CPU callback, it will use the built-in one. Otherwise, you implement the callback and you can decide your own rule for the built-in policy. There are we use CPU masks to track down like the CPUs that are idle and busy. And of course, you can use that in BPF. So you can either access the CPU mask directly and implement your own idle policy, or rely on the in-kernel selection policy. We have CPU frequency integration. Maybe Joel will cover also this one. So if you have questions, feel free to interrupt me. Otherwise, these topics will be exploded probably also by Joel. We now support, that was added a while back, but we support CPU plugging. So we have ops CPU online and ops CPU offline. If you implement that, you can decide what to do if a CPU goes offline and online. That means we also support suspend and resume, because you can decide, if all the CPUs are going offline and you implement your own methods, you can decide, what to do. If you don't implement them, by default, we would restart the scheduler on resume. So we stop on suspend and we restart on resume. So everything migrates back into the default scheduler for the, I think it's one of the, no, we have a, how's it called? Raphael, help me. We have a hook that is called when the system is entering in suspend.
Okay, so the PM notifier.
Yeah, exactly. PM notifier, thank you.
Even before.
Yeah, exactly. We have that. So when you go to suspend, it will stop the scheduler, everything migrates back into fair, and then the suspend happens with the default scheduler. That's what is happening. We have cgroup integration, meaning that you can access cgroup information from the BPF scheduler. And that's like, yeah, so we have a nice API, but you can also play dirty and just, because at the end it's a BPF scheduler. So if you can add K probe or trace points and whatnot and inspect what you're doing. So you can catch, for example, when a task is moved into a cgroup, either using the nice API or either by adding a K probe and extracting information. That's true not just for cgroup, it's true for everything. We started adding more debugging and tracing. We have this little thing. Yeah, so when you, in terms of debugging and tracing, when you hit an error with the scheduler, you would get a trace like this. Especially when you do something really bad and your scheduler, let's say you have a deadlock in your scheduler or starvation or any kind of bug. So if you have a bug that the verifier can catch, it won't load your scheduler, of course. Like a memory null pointer, the reference, or memory issue, the scheduler won't be loaded. If you have like a runtime bug, such as starvation, or you don't schedule a task for a certain amount of time, the core would automatically kick out your scheduler. There's a watchdog for that. So basically, it's really difficult to make your system unusable, because if you try to do that, at some point you will eat the timeout and your scheduler would be just kicked out. And so this is really useful because, let's say, we were able to catch so many bugs and issues. Like in this case, for example, there was a K worker that didn't run for more than 7 seconds, which is bad. But the nice thing is that we are able to see, like, we get the stack trace and a bunch of information. Like in this case, I see that this K thread was dispatched into this DSQ. The number, each DSQ is a number, of course. And so why it was not dispatched? Like why it was sitting here for 7 seconds? The reason is that there was another task running on the CPU 4. And this guy, of course, can only run on CPU 4, right? Because it's a per CPU K worker. There was this nice guy, yes, running as SCAD FIFO, which was like monopolizing the CPU. So this task didn't get a chance to run. That's because we don't have DL server for SCADX tasks. And so the real-time task was completely starving this one. That's another work in progress that we have. But anyway, that was to show you an example of the trace, and so that we can easily figure, like, if there's a problem, looking at this, we can easily figure out in general why something is happening. And I wish we had something like this for FAIR. We don't have anything like this, right? That we have the soft lookup, the untask timeout, but as far as I know, I don't think we have anything that checks, that tells you if a task hasn't been dispatched for, I don't know, 5 seconds. I don't know. So, yeah.
So the soft lookup is still task
You just have to analyze trace points.
Yeah, you can use trace points.
I mean, you get the information, you get the wake up, and then you see it's not scheduled, but you see what's scheduled on it, etc. so you know what's occupying the CPU. It's not that hard.
Yeah, I mean, we have the tools. Yeah.
Yeah, we have the tools, so I don't need BPF for that.
No, I'm not saying that.
Might be, so before the DL server, we use the install D, which is essentially a US-based monitor that checks the bug.
And it's checking like for...
It actually now has also BPF extensions, so it's essentially doing the same. And I guess what we're gonna do is to maybe keep it just like a monitoring option, because we have the dedicated server, but yes, it's able to speak.
Yeah, I see. Yeah, that's
But you do have the story task detector, and this will pick it up.
Yeah, but
if you run trace-RT on it, you have RT tasks running all the time, and storing FIFO tasks for like 10, 20, 30 seconds is not uncommon.
Yeah, but the thing about the stall tasks, I mean, it would get... you're talking about the hunt task timeout, or is something different?
No, hunt task.
The problem with hunt task is that you detect that when a task is actually waiting.
Yeah, it has to be in D state. That's uninterrupted.
Like if a task wants to run and is not even sleeping, like it just goes, but it's not dispatched for any reason. In this case, because there was starvation because of RT tasks. Yeah, you can use the trace points and analyze the traces and figure out when it's happening. But what I'm saying, you don't have a push notification that tells you.
But if you have a wake up and it's running, it's not on CPU, you say hunt task will not pick it up. It has to be in D state.
Well, so this isn't about home tasks only. What we're saying is when you have a task that's in a running state, it just never gets to run.
Right.
So I guess it's a timeout saying, hey, this like the DL server kind of does that too. Like that's what it looks for. It's like, hey, you guys, this guy's dull. Like, it wants to run, but it hasn't gotten CPU yet. Then it triggers. I don't think, we don't have anything automatic right now that says, hey, this task hasn't run in so long. I mean, we have things to detect that there hasn't been a schedule in a long time, but if you have like 5 real-time tasks just round robbing each other, preventing one task from running, I don't think we have anything that says, hey, this task hasn't run, except the DL server kind of is.
Yeah, we can use the DL server, but this is like, we don't have something that I can easily use that gives you a push notification like this one.
But wouldn't this be a soft lock in this case? If you have a shed FIFO task that is watching the CPU for more than 4 seconds or so, will the soft lock detection?
Yeah, but soft lookup
if you're in kernel mode. You have to be spinning in the kernel.
Yeah. This one is different. It's actually waiting. It's not even. I mean, you may have something else that is spinning on a CPU, causing the soft lookup, but and starving other tasks.
Now, if you had like a sched other RCU task that would say, hey, I haven't run in a long time. If you had something like that, like if sched like RCU. Was like pushed like on a thread, instead of doing soft IRQ, a thread. I think we do have threaded.
Yeah, if you don't run the RCU thread there, you'll run out of memory and hang everything.
Yeah, so basically
it's already
it's RCU thread, but it also will say, hey, you get the stall message.
Yeah, there could be another watchdog or something that detects, that just needs to run every so often in CFS.
Like, I think it's like 26 seconds. It has running 26 seconds. Like, hey, there's something wrong here.
Even with the DL server, it's like the little slice that it gives you might not be enough to schedule all of CFS, and so you could have something waiting for a very long time.
Anyway, so that happens. The previous trace is happening because so schedx is implemented as a new scheduling class that runs below sched normal, and actually, what can happen? So when you load a BPF scheduler, by default, it moves all the sched normal, sched batch, of course, into the X class, so they become schedx tasks. But there's a special mode that is called partial mode, where you load the scheduler and it doesn't migrate anything into the schedx class unless you explicitly migrate via a sched set scheduler. And that's provided. We don't recommend using that just because if you have a sched normal task that is hogging a CPU, it would starve the sched task. So you get a stall and people are like complaining because, hey, why did I get a stall? It doesn't work. And that the reason is not inside SCADX, but it's because like scheduling classes can completely override each other. And for this, we need another deadline server that would guarantee that like fair cannot starve the X classes. And once we have that, the partial mode would be more usable, I think. Because otherwise, right now, if you want to use partial mode, you need to physically isolate the CPUs if you want to prevent this problem.
Or use the DL server. I guess the DL server could like then say.
Yeah, that's what I'm saying. Like once we will have the DL server.
Not the DL server. No, I mean a DL server that handles.
Oh, you mean a special
host,
DL?
Host DL server right now. Make sure that CFS or the SCAD or SCAD normal schedules.
Yeah.
You could do the same thing for a DL server, making sure that the SCADX gets a percentage of the CPU, so it doesn't get starved.
Yeah. That's what Joel is working on.
Yeah, we posted patches to do that like 2 days ago. But
yeah, it's working under review.
But
They're refining.
There's some.
I've been at a conference. I haven't been checking my email.
Yeah.
I think on your slide, shed idle, right? They run in the fair class.
Sorry, shed idle?
Shed idle policy runs in the fair class, not in the idle.
Yeah, that's right. Yeah. Well, actually, no, it runs it has its own scheduling class.
You're talking about some the different.
No,
there's
but
two idles. There's shed idle.
But
Yeah.
shed idle is the policy which runs in fair, and then we have the shed idle class.
Yeah, I think some of the shed idle class.
This is the that's correct. Yeah, thank you. Yeah, of course, idle runs below X for obvious reasons. Let me see. Did I miss anything? Oh yeah, I want to talk. Think about compatibility. So this is something that comes from BPF. So BPF itself, doesn't have EU API restrictions. It's a pure kernel to kernel interface. So that means it's really easy to basically do whatever we want in BPF schedulers, which is a bad thing and a good thing at the same time. But there are certain capabilities, the core feature of BPF, that allows us to insert in our schedulers like checks to see, I don't know, for example, if a symbol exists or if an enum contains a certain value. Stuff like that. So the whole core helps a lot in terms of portability and compatibility. We can change API and at the same time provide like hooks or pre-processing macros or whatnot to maintain like backward and forward compatibility. And this like, again, it's a bad thing and a good thing. It's a good thing because it gives us the freedom to refine the API, even if we decide, okay, that's the API, but we want to make a change later, we can just provide an additional API and maintain a compatibility layer for a while. And then after a few kernel releases, we drop the compatibility. So that gives a smooth transition. Yes?
Yeah, regarding the warning that you showed earlier, that case is easy to catch because the RT task was monopolizing the CPU. But say it had run for, say, 7 seconds. And then you are switching between two SCX tasks. And you see that one SCX task has now switched in, but the other has waited for a long time. Then it would appear that, oh, I was running an SCX task for so long. But that might not be the case too. So it can give some false positive.
You mean, so you're saying I could check when an SCX task is running? Or
He's saying that like the RT task running will start SCX, but whereas SCX is not responsible for the scheduling issue, but it's still counting the 7 seconds, right?
It's counting what?
It's counting the time. The time is moving forward. The 7 seconds. So maybe out of that 7 seconds, 5 seconds was because of RT. So he's saying that because of that, it looks like a false positive.
Yeah, exactly. That's why, like, most of the bug. I mean, we received a lot of bug reports with the main schedulers because of this. Because people are running like, I don't know, there are certain distributions or certain applications. Wayland, for example, Wayland runs as SCAD FIFO, or there are drivers that are creating SCAD FIFO tasks. So what happens, like people started to use SCADX and they received a stall like this one, and they open an issue on GitHub saying, oh, the scheduler is buggy because look, it's starving a task for more than 7 seconds. And then the first thing that I see, that I check is I grep for RT-sched. And when I see that, I'm like, okay, it's not a bug in SCHEDX or in the scheduler.
So I would say it's not a false positive because it's like SCHEDX was not smart enough to boost itself or something.
Right.
Like it should have handled that.
Yeah, but you also have that acquire release callbacks, right?
Yeah, I mean, it's not always a problem with the BPF program. Sometimes the kernel can have like this kind of, some kind of bug that is preventing. Stall is just a report. It's not.
Yeah. Yeah, but it's still like annoying that we get so. I mean, we need to prevent this from happening because otherwise it's a maintenance pain. Especially when if distro are starting to use this stuff, it's going to be a pain. So upcoming features, there's a lot to do. Like it's upstream, but there's still so much work to do. One thing that we found this is in 6.14. So on some Intel machines, sometimes we almost eat like the soft lookup in certain cases because we are using a single CPU mask to track the idle CPUs. So if you have a system with many CPUs, like all the writes into the single CPU mask are really hammering the cache, and that can be a bottleneck. So I posted a patch, now it's in the Integions branch for 6.15 that is like splitting the single CPU mask into multiple per node CPU masks. And like just with this change, like a kernel build on an Intel machine, it's a kind of I reproduced this on a kind of an old Intel machine, but just with this change, I was able to get like a 7% boost on the kernel build, parallel kernel build with this change. So that's something that right now it's optional. By default, it will still use a single CPU mask just to have a smooth transition. But once we verify that it doesn't regress anything, we will probably flip over and use the per node CPU mask as default. Yeah, that's another thing I'm working on because right now, again, there's a built-in idle CPU selection policy that has some topology awareness logic. So it tries to prioritize, for example, full SMT cores over partially busy SMT cores. Or on wake up, when a task, when you select a new CPU, it will try, of course, to prioritize the previous CPU or a CPU on the same LLC node or NUMA node. This is all built-in stuff. And right now, you can either rely on that or implement your own policy. There's no in between, like you either re-implement the whole thing or you rely on the built-in policy. And I'm trying to provide a new API so that you can refine this logic, like you can pass flags or an additional CPU mask to say, for example, I want to use the built-in policy, but just on this subset of CPUs. And so you get, like, you don't have to re-implement in BPF the whole topology awareness stuff, and we can reduce code duplication. Because like most of the schedulers now are just re-implementing the ops select CPU just because they don't want to use the built-in policy because it's like they don't have much freedom to take decisions. So that's something that I'm working. There are some, I think last patch is V3, so now hopefully it will be merged for 6.15. These are all things that we are experimenting, like the GPU awareness. Try to keep tasks close to the CPU in a multi-GPU machine. Try to keep tasks close to a GPU. This is not something in the core. It can be probably addressed in the user space, either the Rust libraries or C bindings, whatever. It doesn't need to be in the core. EIS, energy aware, something that we need to explore. We haven't done anything. It's a completely new word on the SCHEDX side. Again, you can do user space thing because you can collect some information from user space and populate some BPF maps. But it would be nice to have some core functionality for energy-aware scheduling. Changgu added recently a trace point, so now we can, because like if you try to do silly dumb things on the BPF scheduler, like trying to schedule a task on a CPU that cannot be used because of affinity restrictions, you would either get an error, or the core would fall back into a CPU that can be used. And this is transparent. You don't have visibility of this in your BPF scheduler, or rather you didn't have visibility. Now there's a trace point that you can use to catch these events. Like when the backend is doing something against your decisions, you can use the trace point to determine when it happened. That's also done. It will be in 6.15 when Taejun sends the pull request. Yes, that's another big work in progress that Joel is doing a great job with the DL server, because it's something that we need for the reasons that I was saying before. Something that I would like to explore is the CPU idle integration. That's another question that I have, because I just don't know. I don't think we have anything in fair.c where you can say, for this CPU, I want to prevent going into deep idle state. Do we have anything?
There is something at wake up, but it's not very functional.
Okay.
Yes. PMQS.
PM, that's the only way that we. Yeah, it would be nice to have kind of an API in SCADX to interact directly with CPU idle. One thing that I noticed doing some experiments on an ARM64, for example, is that when the CPU goes into deep idle states, it's very expensive. So I was running some Llama benchmark on an NVIDIA machine, and at some point I tried to do a trick where so in SCADX you can kind of implement idle polling, but for certain CPUs only. It's like kind of passing idle poll equal, 1, but only restricted to certain CPUs. And when I did that, I was getting like 8% performance boost on this Llama benchmark.
What would be wrong with using latency QoS for CPUs?
Using, latency
QoS?
QoS?
Latency QoS, like PMQoS. It's just...
maybe that's... Maybe that's...
There is a system-wide PMQoS, DMSU, and there is a per CPU.
Okay, that's interesting. I didn't know that. That's good.
But do we want guidance across well?
Yeah, but it would be nice if the scheduler could say, okay, I'm running a task that has strict performance requirements. So even if it's sleeping, I want to keep the CPU alive.
No. So this is a property of the task, and idleness is a property of the CPU. So don't confuse one with the other.
Yeah, I know.
Task migrate.
Yeah, but it's kind of like the CPU frequency. Like I can say, okay, this task is important. Let's max out immediately the CPU frequency.
No, but by the time your CPU wakes up, it may not be running this task anymore.
But it's up to the scheduler.
It could have gone away from it. So.
Yeah. I mean, I can do the trick and keep.
Even for a high-speed PMQoS that it can do from let the scheduler decide when it wants to put have a CPU have low latency wake up, right?
But you can already, with this PMQoS per CPU, you can select, say, I want to wake up latency of 10 microseconds, 1 microsecond, and that's it.
So you can say that the time, right? You want one. Okay.
It's a wake up latency value.
Okay, I need to look at that.
But the idle governors also look at the timer.
Yeah.
So if you look at the timer on that CPU, it should go through the virus there.
Okay, that's interesting.
The CPU idle governor takes the timer and this wake up latency. So normally you don't have to go inside the CPU idle.
Okay, that would be nicer than kicking the CPU artificially in SCADX, because it works, and I really get like 7%, 8% performance boost, so it's worth it. But it's kind of ugly. I want something more refined. Yeah, last thing, and then I'm done. Like there's also SJ is also working on Damon to try to classify tasks. That could be interesting in general, and we were planning to use this information to say, you know, that's a cache-sensitive task versus this is a CPU-intensive task. We don't have anything like that. It's just ideas that we could explore. And that's the most requested feature, the hierarchical C-group scheduling. So being able to load more than one SCADX scheduler, something that I personally don't like, because I think you can already do in your own scheduler all the rules that you want to apply per C-group rules. But I don't know, there are people interested in this. So at some point we may decide to just explore this possibility and have multiple schedulers running at the same time. Whatever.
Yeah, I think I have a general question. So
yeah,
looks like for your features upcoming list, lots of them, more than half of them are essentially, if I understand correctly, replicating features that we already have in the core scheduler and other subsystems. So why do you think it's still worth it going away? I mean, it's a lot of work for replicating everything, and then you have essentially kind of a copy of something that's already there. So why do you think
I'm glad you asked that. That's actually a really good point. It's basically what we are trying to do with what I'm trying to do with and Joel as well, and others, with the default built-in idle CPU selection policy. We end up re-implementing what's in FAIR, basically. So why don't we just use the policy from FAIR? But so we have two options. Like, one is to provide hooks somehow in FAIR that can, to expose certain functionalities of FAIR.c to SCADX, which it's a possibility, but I don't know if it's the best one, because it would add dependencies between the two subsystems. So if we want to keep them completely independent, it's not the way to go, because then we may break, we change something in SCADX or something in FAIR and it breaks, one thing breaks the other. So the other thing is, okay, let's start by re-implementing what we have in FAIR, and doing so, it would be nice to be consistent with FAIR. Even if there's something, like we found recently that there's an optimization for a K-worker, when you have a K-worker and a per CPU K-thread and a task that is awakened by that, we try to keep both on the same CPU. We did some tests, and in SCADX, it doesn't seem to provide any benefit. But we were still considering to apply that change, just to be consistent with FAIR.c. So because
sometimes, the code you just mentioned, it's really related to a workload, a very specific workload. Yeah. Somebody figured out over maybe 2 or 3 years ago, and then people forgot about it.
Exactly. So maybe that's re-implementing process is a good way to spot, potential improvements for the FAIR.
It's always the case if you have enough people discussing this stuff, right? But what happens if the interest goes somewhere else? Then those things they.
And by the way, this is something that we are re-implementing this, but as a default policy. It doesn't mean that all the schedulers are automatically using this. It's just what's the best default. Then if you don't like something, you implement your own code back, and you can override the default one. But yeah, it's a good point. It's a really good point.
I think we are essentially out of time. Yeah. Thank you.